Good morning to all the participants.
Good morning, everyone. Welcome to day 4, session 1. Where we are with 15 plus years of experience in computer vision, NLP, machine learning, and AI. Currently spans image processing, deep learning, and AI-powered solution for real-world challenges. We look forward to an engaging and insightful session. Sir, we invite you to take over session 1 of day 4.
Okay, thank you for inviting, and thank you. First of all, good morning, everyone. I hope I am audible. Hello. Good morning, everyone.
Yes, sir, you are audible. Yes, you are audible.
Yeah. Thank you for acknowledgement. So, good morning, everyone, and first of all, thank you for joining today's session. In this session, let me share my screen, then I will explain. I hope you are able to see my presentation.
Yes, it is visible.
Yes. Okay. Yeah. Thank you. Once again, good morning, everyone. Today, I'm going to handle. First of all, this session is divided into two parts. One is first I will walk through the technologies which I'm going to explain, and later practical sessions. Because 1.5 hours sitting only listening is boring, right? So I will show you practical how to improve the performance on particular systems. Example, any system we take, classification system, under challenging we make the challenging performance. Today title is challenges in industrial computer vision and way out. So we think that if you see any papers, they will always get the 99% and they will achieve their method is better. But when you come to the deploying stage, ultimately every method fails, because each method is specific to particular domain, right? If we adapt that technique to new data, it's very challenging. We'll end up with getting less data. We will be disappointed. Again, then we need to work out how our new data kind of thing. Desired result. At the same time, we promised to the customer that we know this is very easy, but at the end, when we apply and show the initial results, ultimately we get the bumps, right? So, my name is Krishnarao Kakirala, working as an associate research scientist in AI. 16 years of industry experience in AI. Before jumping into the today's session, I will give you overview about me. And today outline is first I will explain about me and types of projects and data handled in my career. Why I'm going to teach you is so that when you come across the same kind of issues with the data, you know how we can mitigate those things. And challenges in industrial computer vision. One second, let me. One second. One second. Laser is not there. Let me show. Oh. So challenges in industrial computer vision, and then we go to the objectives of today's session, and one of that is issues with the data imbalance. and handling techniques. I will guide you through two techniques. One is augmentation and class balanced loss function, and I will also tell you where to concentrate when particular issue comes. Where to concentrate, I will guide you also. And some practical sessions, we do small kind of practicals, easy practicals, so that you can grasp the things in one session about them. There are plenty of techniques are there, but I will teach you, walk through you simple technique to understand them easily, and how to adapt them, and how to see the results and the results. Okay. First, about me, I'm having 16 years of experience in handling computer vision, IoT data, NLP data, and realizing applications by using this data by using machine learning, deep learning, and generative AI. Okay, and augmenting data analysis workflow. That means not only building the application as a POC. First, we build the application to prove the concept that it is working. Later on, main things comes optimizing the things, and how to automate the data flow workflow. Suppose when we do, what we do is we do load the data manually. Okay, manually load the data, and some applications we manually run, and the output of that application, what will happen again, we store, and we build another application, we feed that, manually feed to the other application. But here what we do is we need to do end to end. Just what we need to do is we give the input, that's all. It will do end to end pipeline, and will fetch the output results. Okay, I will tell you with example of what is that end-to-end pipeline. And handling large data sets. In industry, there are two kinds. We won't get uniform data set. Always we get the large data. Okay, it is unstructured data, unlabeled data, large data sets, and imbalanced data sets especially. This is the main cause in industry. Everyday industry, we face this kind of challenges, imbalanced data. How to handle them easily, and design and deploy scalable cloud-based solutions. See, if you build any application, what we are doing application on our PC, it will be like a standalone application. But when we deploy this into the cloud, suppose you want to provide it as a SaaS. SaaS means service, okay, as a service. Then many people across the world will use that at the same time. What will happen? It will stuck, or it will collapse. Okay, how to make it scalable? So that means cater the service to the many people. Okay, that is scalable application. And delivering insights through data driven methodologies, not only getting the results, how it is doing, and on what basis the algorithms are making the decision. Okay, that is main important to when we come to the customers. They will ask how it is doing, and on what basis it is taking the results and getting the insights. Okay, making the predictions. And my core competencies are strategy planning and leadership. Okay, now earlier I will tell you, and project management, research and development, reporting and dashboards, client stakeholder engagement, and team building and management. Okay, not only that, apart from that, I will act as a in few of the projects, I will act as a developer and co-developer. Okay, because if you want to understand how the technology working, we should always keep in our touch in the development part also. As we grow our career as a manager position also, if we keep in touch with our technology, then it will be a beautiful understanding of about the technology, and whether we can solve customer given new problems. Okay. Notable achievements are 16 granted patents in US, Japan, and India. Awards are industry level 3, and ideation awards are 1, and 14 IEEE publications, tens of successful project deliveries with high customer feedback. Now, if you see at my technical career transition, I started as my career as an engineer in images, videos, text, IoT data. Later on, when earlier we didn't use machine learning. So, like in images, blob detection kind of thing, measuring their sizes. But later on, when complex problems comes, making these kind of things, it's very difficult. Later on, we adapted machine learning, deep learning. Okay, so and generative AI, now generative AI. Based on the generative AI, we started building AI agents, AI agents, and then making agents scalable. Okay, scalable means suppose if you develop any particular item, okay, particular project, one is scalable with respect to the applications, and other is with respect to the data also. scalable. Suppose if I make recently I developed AI agent based on the creating the advertisements, okay, automatically advertising about the particular product. So what we do is we build the system by analyzing each component on the particular product. Okay, let's say we have built the product advertisement for the Cerelac. So how to make work this product to the other brands? Okay, not only Cerelac, like the biscuits kind of thing, biscuits and so on. So how to make this work to scalable to the different kinds of products? Okay, not different kinds of products without investing much time on changing to the new product. Okay, with less efforts we need to adapt the system to the new kind of product. Okay, that is the scalable solutions. This is about me. Now, type of projects and the data handled in my career are with respect to, especially 90% of my work on handling images and videos, remaining 10% text, okay, IoT data. Of course, that when you are a researcher in machine learning and AI, no need to worry of the data, input data. Only we need to worry when you apply pre-processing and those stages. But at the end, our is numbers only, irrespective of data. Our input is numbers only. We need to handle with numbers, okay, to make it realize our product. One is classification problem and object. In classification also plenty of classifications algorithms are there, we see as a classification, but underlying there are a lot of different kinds of classifications are there. And object detection, here also different kinds of objects we handled. And anomaly detection, let me remove this to okay, anomaly detection. In the anomaly detection, what we do is product, whether it is good or bad, we decide that. Okay, once it is decided the product is good or bad, and what basis it is deciding. Okay, that means localizing the anomalies in the images also important. Okay, and the localization, in the localization, two things: anomaly localization as well as object localization. Once we find the object localization, we need to measure the particular properties like dimension and diameter, okay, and the size of the things. And while after computing these properties, we need to compare with the neighboring, and a lot of distribution we need to come across. Local localization and the tracking also. In the tracking, it is one of the project. It is percentage identification across the different cameras. See, when we see face recognition, for example, what we need faces, right? But always in the CCTV footages, it's very difficult to track localize the faces. Sometimes it may be behind also, sideways also. It's very difficult to identify the person based on the faces. In such cases, what we do is we apply the percentage identification. Suppose, let's say, I have 4 camera feeds. From the first camera feed, what I do is I want to tag this person where and all he moved in our company factories. Okay, we need to log the data also. In the same, suppose if we deploy same system to the colleges, what we do is we put the cameras at different places, and we localize. Okay, we track particular person, one particular student or faculty, where he knows, where he moved in the departments, and we can easily grab those things. Okay, we can later we can use them for analytics kind of thing. Okay, and the generation kind of thing. See, here we may see that generation won't be there in industries, but it is there. Image generation. Why we need image generation is when customer comes with only 1 or 2 images. Okay, those images are not always helpful to make the decisions. What we need to do is we need to generate similar images. Okay, to build the robust system. Okay, one way you can think of the augmentation. That is one. The other thing is we have, let's say we have 2 different ICs, into IC chip 1, IC chip 2. Okay, if you want to transfer the characteristics of IP chip 1 to the IP 2, then we need to use these kind of generation methodologies, so that the customer benefits, saves cost, time to make similar ICs. Okay, and find deploying into the investigation and analysis system. This is with respect to the algorithms where I worked on, and with respect to the data types. Not only data means all three types. Text data is there, and images, videos, IoT data. But in the data itself, there are different kinds of what kind of data are available. One is minimal data. Sometimes customer will give only one or two samples, so we need to work with build the system around it. Okay, that is minimal data. Next is imbalanced data. Suppose if you build any classification system with the 10 classes, okay, but existing algorithms, what you say, if you first blindly will try existing algorithms, but ultimately you end up with less accuracy. Okay, so then you will try to put apart how what is the problem, and you will start investigating what kind of data it is there and those kind. So here imbalanced data especially means, suppose if you have four classes, if four classes having equal number of images, that is called balanced data. Okay, imbalanced data means some classes having 100 images and some classes is having one or two images, right? So that is called imbalanced data. And the thing is noisy data. So you may be surprised here. Noisy data means images with wrong labels. That is called noisy data. Okay. Noise labeled data, we can call it as noise labeled data and noisy data. Because what will happen is when images are collected by customers, they are not technical experts, right? So what they will do is different people will collect the data. So they will label the each data based on their opinion, not with respect to the algorithm and those things. Their opinion. Each person has different opinions. So based on their opinion, they will label. Suppose one person labels as a good, another person will label as a bad. Okay, in bad also. Okay, that in that case, if you blindly feed that data to the our existing algorithms, it will learn misdata, right? So deep learning means whatever the we feed, it will try to learn from that data. It won't have intelligence to adapt that. Nowadays it is there, but if you look at the basic architectures and those things, what will happen is it won't make the decisions. It will learn what we feed to the network. Okay, suppose if we teach, if we try to teach the new kids, what will they will try to learn what we teach. They won't decide whether it is good or bad. In the same way, these deep learning architectures, what we feed, it will try to learn that. Okay, it won't make things, but at the beginning of the training process, it will learn the good data, but as it goes, it will try to force itself to learn the bad data also. Okay, bad data means bad predictions you will get. So that's why to eliminate that problems, how to eliminate such kind of issues, we handle that noisy data. And the other is structured data. So we have particular one. If structured data very easy to handle, but whereas unstructured data, suppose structured data, if you compare, it's a tables. Okay, that is proper structure will be there. If you take columns, this is all integers and all structure. So those are structured data format. Unstructured data means if you write table information in the form of paragraph, what will happen? It's like a unstructured data. Okay, so text it will clubbed with the text and digits and kind of thing. Unstructured data and multimodality data. Sometimes we'll build algorithms. It will understand multimodality data. Okay, multimodality data means here, suppose you will have videos and sensor data, and not only sensor data, speech, acoustic emission signal. Okay, these three signals are there, three data points are there. You need to build the single algorithm to understand these three as a input and make the prediction out of it. So one example is in the one of the project we did is anomaly detection, okay, of the welder component. Okay, during the welding process, because human will adjust dynamically based on the welding procedure, but when robots are doing welding, it will do in the predefined order, right? It won't change dynamically. Okay, because of that, sometimes what will happen is due to the change in the power fluctuations, there might be a change in the welding process. Okay, sometimes it will do light at some places, sometimes it will do correct, sometimes it's over welding. Okay, so to when you capture that as a video, what will happen, you will see the fire only. Okay, welding fire, it's not possible to see welding component clearly. In such cases, what we do is, along with the videos, we also try to capture acoustic emission signal, that is sound signal only. So the sound signal will capture the welding sound. So sometimes based on the sound also we can decide whether it is doing giving good or bad, right? So that kind of thing. Okay, so suppose in our home fans are rotating, so initially it will do good, but later on it will give the sounds, okay, bearing failures or something else. So our ears has capability to understand that and will make the prediction. In the same way, here also the acoustic signal captures welding procedure. So based on that also we need to make the prediction. So that means we need to use acoustic emission signal, and as well as acoustic emission signal, as well as we have videos and other sensors also, temperature sensors, those. How to handle these three as a input and make the single algorithm to make the predictions. So that is called multimodality data. And the thing is sensor data, like acoustic emission signal energy and the temperature sensors. And if suppose in the Toshiba has one of the manufacturing unit is transformers, okay, electrical. While analyzing those transformers life of transformers, those things, they will fix different sensors, oil density, okay, oil density measuring sensors and heat sensors, and cameras also will be there, okay, cameras and different kinds of sensors to track, okay, to track and to predict the health of the transformer. Okay, so here we need to handle those sensors and building AI application around it to make the prediction. Okay, here these are the different kinds. There are plenty are there, but high level I have given these things. Again, inside this there are so many variations are there. Okay. Okay, these are the different kinds of project areas and data handled in my career. Okay. Not only that, there are other things are there. We see them in the few future slides. And the main, now we see what are the challenges in industry image processing is, if you see the academic and industry differences is algorithms are same, okay, algorithms and what we are using algorithms and industry are used, but where we do is data sets. Okay, initially if you want to build any model, what we do is we will build the neat, okay, clean and neat and balanced data sets. For example, if image classification, 10 class classifier having equal number of and enough number of samples, okay, to make build the deep learning architectures, right? So that is generally academic research will work on. Okay. So most of the academic research, but if you come to the industry data, it will has highly imbalanced. Okay, that means sometimes we have more, some classes having more number of samples and some classes are having less number of samples, hardly one or two. Okay, so imbalanced data. For example, if you want to build the anomaly classification, whether particular welding or particular steel plates are produced in the better quality or not. So we always try to make the system to produce the better, right? So that means we try to get the better output. Sometimes due to a lot of parameter changes inside the process, okay, during the process causes sometimes hardly anomalies will come. Okay, so that means if you want to make algorithm to build at the output of the our production, what will happen is we have very good samples, high ratio, and less samples are very less. Okay, so then we need to build. Okay, so in such cases the data prepared would be imbalanced data. And the second thing is noisy data. As I told you earlier, I explained here, suppose for example, here RC is labeled as cat and 7 is labeled as 0. Similarly, the here to understand I put this, but when you see the steel plates, because I am not allowed to put industry data here, that's why to make them understand, I will put general Google collected images. So here, because when you see as a human eye, what will happen is we are very confused about to assign which class, this one. So that's why while taking decision, they will assign something. Okay, so that is called noisy data. And not only that, once you build the application, speed is important, because when manufacturing process particularly, it will be very fast, right? So we need to build the system which meets their speed. Otherwise, what will happen is if our machine takes longer time, we need to keep the product till it recognizes. It will take longer time. Because of that, it starts accumulating one by one. It will disturb entire process, right? So we need to build a system which meets the real time. Okay, so that is another. Under scalable solutions. So how to make for one kind of data, how to make another. Similarly, customers and minimal data. Minimal data means we have very less data sets. So we have, see, in one of the project we received hardly only one digit, single digit samples. You initially we struggle to find the build the solution around it. Later on we managed to reach the customer expectations. That is minimal data. Sometimes they won't give any training data. Okay, they will have test samples, build the algorithm on these test samples. That's it. Okay, so initially we worried how to build without training data. Okay, because till then we have used only supervised learning algorithms. When this problem comes, we shifted our thought processing and moved to the unsupervised learning kind of things to make the existing algorithms pre-trained models, make pre-trained models to work for the unseen data. Okay, that is called no training data will be done. And another major crux is inter-class variation is very less. Okay, so that means suppose if you see steel in steel manufacturing, our one of the project is grade assignment. That means once output steel is produced, what we need to do is once output is produced, we need to assign the grade. Okay, there are according to the standards, there are 0 to 12 grade numbers are there. Based on the output of the steel, we need to assign grade different grades. We need to assign one of the grade number to producer steel based on the internal structure of the steel. When you visit any steel vendors, what they will lay out each steel's places. But when you see as a human eye, you will feel that even garments also, when you visit if you buy the some items at top shops, cost will be high. But when you buy, if you buy at roadside shops, cost will be very low. Because there but if you see that, you will feel that those are similar. But when you wear and feel it, and durability, the quality might be different. How the quality will be judged as a human, it's very difficult. But there are a lot of parameters to assign the grade, okay, quality grade to the steel images. Okay. In such cases, that variation between neighboring grade will be neighboring grade steels will be very less. So in such case, how to handle them? First, we increase the separability and then build the algorithms. There, we need to majorly work on input data side. One part. Okay, these are the different challenges in industry image processing. Okay. Now we jump to the, you may thought that why this information is required, because as a researcher I have seen these many problems, right? In your field also you might see similar kind of data challenges. Because algorithms, if we read it, we get, but when you see the data point of view, it's very difficult to see such many such types of data, right? So that's why I have given this introduction about different projects that I have handled in my 16 years of career. Now I jump to the today's main objective. In this session, you will gain some insights about understanding imbalanced data, because there are a lot of types are there, right? Out of that, I picked one, that is imbalanced data. Most of our problems will be similar to imbalanced data in here also. Okay, understanding imbalanced data. What is imbalanced data? Why industry always contains imbalanced data? I will explain why any data set initially ends up with imbalanced data. Okay, and how to identify imbalanceness in the data. Okay, and hello, am I audible? Yeah, okay,
Yes, sir.
yeah, fine, thank you. Because I am talking to PC, right? So in between, I try to ask. This is my, even with the customers also, I try to interact in this way. Okay. And identifying imbalanced data. How to identify? Suppose once you get the input data set, so because initial days we blindly build a algorithm, we feed the data and build the algorithms. But once you know this thing, then later onwards, first every now what see now every industry, if you consider, what they will do is once they get the data, they will do EDA, exploratory data analysis. Okay, so why they will do is to avoid that kind of because in here for everyone time is important. So to make time efficiently, first we do the data exploratory analysis. Okay, whether it is imbalanced data and those kind of things we do. That is one way to identify imbalanced data, and strategies for handling imbalanceness in the data. So I will explain two strategies, but I will give you overview where and all the strategies can be applied. Okay, how to build a new strategy where and all in the entire system. I will give you that also. Okay, handling imbalanced data, and we see some imbalanced methods to overcome the issue. Okay. So first is to understand the imbalanced data means imbalanced data occurs when a distribution of the classes in the data is not uniform. For example, this is my data, 5 class data, 6 class data. One class is having around above 70 images, and another class is having less than 10 images. Okay, if you see the distribution, this will be imbalanceness in the data. It displays there is a huge imbalance, not only some small imbalance. There is a huge imbalance in the data. So this is what imbalanceness in the data means. Okay, and the issues with the imbalanced data is, suppose if you blindly build the algorithm, okay, initially, then how to understand? You will see, okay, training is doing good. This whatever the session I'm handling is with respect to the deep learning. Okay, deep learning things. So when you try, any model is trained, what will happen is you will see that training accuracy is keep on increasing. Okay, and but when you comes initially, the test accuracy and test data is keep on increasing. Later on, it is decreasing. Okay, so that means this will overfit the data. Okay, overfit this will overfit the training data, but fail to predict the same doing showing the same performance on the input data. Test data is failing. Okay, so that's why this overfitting comes into the picture. To avoid this, generally people what they will do is initially they will stop. So where performance of the on the test data is decreasing, we stop there. But that is not the solution. Early stopping. Okay, but version 1 it is fine, but version 2, version 3 onwards, we need to try to build the other algorithms on top of this. Okay, overfitting. So this is one way to identify. And the thing is loss. When you see the loss and the training loss and the test data is keep on decreasing. Okay, as a number of efforts increases. But when you see the loss on that validation test set or validation set, if you see, initially it will try to decrease, but as well as when more learning happens, what will is, as I told you, it may be then due to the noisy data, or maybe it may fail to predict, because it will initially, because when you see variations in the data, it will try to adjust that. But as number of epochs increases, what will happen is it will try to assign the class of the major number of class with higher number of samples to the it will assign corresponding class to the other classes also. That's why in this way it will try to it will bias to the classes which having higher number of samples. So because of that, the loss on the validation is keep on increasing. Okay, so this is because of one is bias and overfitting. This may be due to imbalanceness in the data issues. Okay, once you suppose if you forget to do exploratory data analysis, then you will need to do analysis on the output plots. Okay, output plots to decide what kind of data as input. Okay, these are the issues. Now you see why industry always, you may think that, see, initially we may think that why can't we collect equal number of samples for each class. Okay, so you may think that then problem will be solved, right? But in industry it is not always correct, because I will tell you why. One is it's not always possible. You may think why it is not possible. Okay, the solution main reasons are, one is time is important, and the second is cost. Okay, I will explain with example. I will share my experience why cost is important. And the system state. Okay, while manufacturing process, the systems behave at a different times at a different things. Okay, system state. That means you can think it as a system settings and electrical fluctuations and the chemical composition. We see one by one with one example. Chemical composition and material properties. Because of this, it's not always possible to produce equal number of images for each class to build the AI system on that. Okay. See, time. Why time is important is sometimes machine takes a longer time to generate samples. Okay, for example, in textile industry, what it will be is to want to if you want to find the quality. Okay, build the AI system to find the quality of the particular fabric, or you want to find anomalies. Okay, you want to detect anomalies on the fabric. Okay, so that is, let's say, two scenarios. In the two scenarios in textile industry, how the fabric will be made is once first threads will be made and the color composition and the texture composition. This is the entire process. During this process, there may be some pauses to dry out fabric kind of thing. Those things, right? So it takes almost most of the time. It will take longer time to produce the output fabric. Okay, once you have produced it, so this is very good. So when you take second fabric, say there is just some problem. Okay, if you want to reproduce same problem, it's very difficult using the machines, right? So here our application is to build a to categorize. Okay, to categorize inside anomalies there are different classes. Okay, this is one fabric. This is kind of, see, in the textile industry there is a blobs or scratches are there. Okay, felt fabric. So again in anomalies different kinds of anomalies are there. So if you want to reproduce such anomalies, you need to change a lot of things in the system. But again it will be skeptic about output, right? Okay, that is the one process. Time is important. Second thing is the cost. Okay, so in VLSI industry, if you want to make the fabric, you need to invest a lot of amount. Okay, vapor, not fabric, sorry, vapor. If you want to produce the vapor is the process of making the layers on the IC, right? So if you want to produce those kind of vapors, you need to invest a lot of money. Okay, and that too, when vapors are delivered, it will be delivered as a batches, like millions of vapors will be produced. So during this process, if you change the adjustment in the system to produce the anomalies, lot of amount will be wasted, and a lot of changings will be lot of time will be wasted. So that's why people are not interested to generate such kind of samples. That's why where the cost is matters here. And the second is system state. So as because of aging of the system, okay, there might be a lot of changes in the functionality, like bearing failures and maybe some threading spring failures. Because of that, there will be a changes in the behavior of the system. Because of that also, these anomalies or maybe fault products may come out. Change these things. And the electrical fluctuations, as I said, during welding, robo welding to the cars, one of the product we made is welding anomaly localization for car welding. The customer is Germany based company. Okay, what will is when car door is welding to the doing, there are different parts will be there. At the different parts, four robo arms will be there. Those arms will simultaneously do the performs the welding. Okay, when it performs, sometimes due to the floor fluctuations, one of the arm will fail to weld. So in such cases, we need to identify that. So reproduction is very difficult, because make the one arm to failure and repeatedly and make the welding means your product will be wasted, and as well as this adjustments will be very difficult, right? Floor fluctuations and chemical composition. So especially in the textile industry and in the same IC chip manufacturing and steel production also, these chemical compositions will be there. Suppose in the steel industry, once we receive the raw material, raw material, what we need to remove the unwanted materials from there, impurities from the air, and at the same time, during the heating process, so we need to release a lot of gases there. So there is a chemical composition. Suppose if there is a change in the ratio of the gases we release, there will be a fault. Okay, so we need to continuously monitor them also. That is another application, AI application, to monitor whether equal ratio of gases are releasing or not, desired ratios. Okay, so during the chemical composition also, there is a problem in the producing the faults and the anomalies. Okay, under different grains also, the steel grades. Because of these things, there will be a result in the different grades of the steels. And another thing is material properties. Okay, especially in the VLSA industries, making the vapors. Okay, so making the vapors, different kinds of, especially these vapors are made from the silicon, right? Silicon means sand. So what are they using? There may be a changes in the material properties. Again, inside material properties, if you go into the deeper, again that is a problem of chemical composition. Okay, but at the outer side, if you see, there is a different qualities of the steel. Again, there is a, because of material properties, there will be a change in the quality. Because of change in the quality of the material, there will be a change in the end product. Okay, so these are all the reasons behind producing imbalanced data in the data set. Okay, so now how to mitigate the issue, because these are not in our hand. Okay, producing the equal number, then where we need to concentrate, in the architecture level, or making increasing the only at the synthetic data, creating the synthetic data, that is one approach, or working on the architecture level, or working on the loss level. I will show you where we need to stress, or where we need to fine tune the algorithms, where we need to concentrate, what are the different locations where we can put human efforts, okay, enlist effort to increase that. Okay, that is one. Now, how to identify imbalanced data? Before going there, how to identify imbalanced data is visual inspection. Okay, that means you can see here, if you see class imbalance, these are the cats are there are 6 are there. Okay, dogs are 2. This is human eye we can find, but when we get the different kinds of non-image data, okay, so then only thing is we need to do the statistical measurements. Okay, otherwise plotting the distribution of the each number of samples, and doing the some statistical analysis. Okay, one is loss and these things, and another is drawing the computer matrix, and sometimes we need to compute the statistical parameters like variance, mean, and skewness, kurtosis. So we might read these during our academic, but we don't know where we applied, right? But when you come to the real time, you come to know, okay, here we use these parameters. Why these techniques are needed. Now, once you do practical examples on that, you will understand. Okay, these are required here because of that. These parameters we learned in the academic. Okay, these are the statistical parameters we do. And the second here, this is how to identify the small examples. There are other things are there, that is broadly comes under statistical measurements or visual inspection kind of thing. Once you plot, again we do visual inspection only, right? Okay, those things, identifying imbalanced data. Now we come to the solutions. Okay, now we feel that once you receive data, okay, it is impossible to build the system with the imbalanced data. But when you start doing brainstorming, a lot of discussions with the technical team or colleagues kind of thing, then it will be possible. Okay, so that means as any system, we have control at different places, right? So we think when problem comes, okay, we'll end up with thinking of it. But when you start really put efforts on thinking, you will get the solution. Okay, we leverage those places. We see what are those places, and we leverage those places to mitigate the imbalance. Okay, so am I audible now? Hello? Hello?
Yes, sir.
Yeah.
Yes, sir. You
Yeah,
are
yeah.
audible.
Okay. So one is at input places, that is one it at input data. That means working on the input data, make balanced data. And the second one is model. Sorry. Second one is working on the model. Okay, we need to do some tunings of the parameters or building the layers. We see that. Second is at model level we can do. Third level is the at output level. Okay, that means loss function, designing the new loss functions and changing the loss functions. Okay, and existing thing, clubbing multiple loss functions. Okay, so at a different, that means we have three places. See, at the beginning we don't have any solution. Now we have some ways to do to mitigate and to handle to mitigate the issues of imbalance. And at the same time, we find three places where we can concentrate to make it work. Okay, so that is now we have three solutions. Now again in these three categories, there are sub solutions will be there. Okay, so at the input level, what we do is one of the problem is how to mitigate issue with imbalance at input level is by applying the synthetic minority oversampling. What we do is, let's say our data is like this. We have blue color is squares are more number of classes, and this green colors, okay, circles are less number of samples. If you build a system on this, you will end up with the bias, right? Okay, to eliminate that, what we do is we create the synthetic samples. Okay, there are methods to generate synthetic samples. That means variation of the similar kind of thing. What we do is we do interpolation. We create new sample as a interpolation of the neighboring samples. Okay, so in that way, these red colors are new synthetic data which has similar properties of the these green classes. Okay, so this way we generate new samples. After resampling, what we do is we are able to improve up to some level. Okay, it's very difficult to reach equal number, but we managed to do that. Okay, so this is how by using synthetic minority oversampling we increase the number of samples. And the other thing is at the same time reverse order. Why can't we reduce number of samples? Of course, if you reduce that, if you have enough number of samples and with huge variance between one class and another class, then what we do is this is the one of the option. But ultimately, this is not best option when we have very minimum number of samples for each class. Okay, so what we do, we reduce number of samples of the majority class. Let's say we have here again blue color, and this is gray color minority class. So what we do is we randomly drop some images. Don't do manually drop. What we do, we need to drop randomly at some places. Okay, we need to do drop, but always try to avoid dropping the points at the boundary of the class boundaries. Okay, so what we do is we randomly drop these things. Again, there are metrics to do this job. Okay, what we do is we randomly drop and start training the model. Okay, these are the things. And the third one is making the argumentation. Okay, this argumentation nowadays we are applying the same argumentation to the text data, scene data also. But when you come to this, majorly we apply for the image data. Let's say we have input image, we generate a lot of variations. Like what we do, we reduce the scale and we rotate dog, and we flip the dog. Okay, and similarly, what we do is we crop some part, we crop. Okay, because human has the intelligence, only seeing the face also it can tell, and seeing some size and some part of the object also we can able to recognize. In the same way, to make the architecture to understand, okay, variations of the input data, we try to do some argumentations. Okay, these are simple image processing only, scaling and downscaling, upscaling. Okay, after that, rotating the object and cropping the randomly crop. Okay, not only center part, randomly crop the object and flip the object, mirroring the object. Okay, both vertically and horizontally. So these are the different variations. In the rotation also, we can rotate the object at 360 degrees. So that's where we do the augmentation. Now we have seen the places. We have seen few techniques. There are multiple techniques are there. These are the majorly used techniques to do the to increase the equal number of samples and to leverage the input data, make it as a uniform. Try to make not 100%. We try to make it as uniform as possible. Okay, this is at the input level. Similarly, if we at the model level, if you come, what we do is another thing is changing here. Let's say we have deep neural network. So what we do is we harness the model. That means number of layers, or number of layers means 1, 2, 3, 4 layers we are having. So generally we consider that as a 3 layers only. So we try to increase number of layers, or maybe number of neurons in the each layer. Okay, what we do is we try to make it work as much as possible. Okay, for this we need to do a lot of experiments and a lot of analysis kind of thing we need to do. Not only that, sometimes what we do is we replicate the different same architectures at the multiple levels. We join the outputs of those architectures. Okay, in that way architecture change also we do to make it work for the imbalanced data. Okay. So this is where what we do is we try to harness the model to get the desired results from by on the input data. So one is input data, second one is architecture level, what you have done. Okay, this is one thing. Because I don't go in deep about these things, I will explain another function. We see some practical examples of that, because understanding this architecture level change requires some knowledge and deep learning architectures, what are the variations, how to use them. Okay, so the at architecture second place. Now at output, now we have seen at input and at the middle. Okay, at the middle means main algorithm. One is on input data. Now in our hand, another option is loss function. Okay, so what we do is instead of using the conventional loss, we try to use other loss functions. Like here one of the thing is class balance loss. Class balance loss means what we do is generally these are the L is the loss function. What we do is we try to weight. Okay, we try to weight the loss function depending on the input data. Okay, suppose I have 10 images in one class and 2 images in one class. What we do is we try to put less weight to the higher number of classes, and we try to put a higher weight to the uh, images with less number of classes. Sorry, class with less number of images, less weight there. High weight. So that means we are telling to the architecture, concentrate on this part majorly. Okay, images with less number of samples. Please concentrate on this. Okay, and make yourself learn about that. Okay, because architecture will learn not itself, it will learn based on the loss. Okay, based on the loss function, gradients will be calculated. These gradients will be used to update the parameters of the learning parameters of the deep learning architecture. Okay, in that way, in the last weighting also there are so many variations are there. Okay, out of that recent best one is the class balanced loss function. So we have used this and we improved the performance from 64 to 96. Okay, we also done some input data augmentations and architectural change. We have improved from 64 to 96%. Still there is a gap, but customer is okay with that. Okay, now still we are doing to make it 99. Okay, this is thing. Okay, this and that means we have seen 3 different places at on which we are going to work on to make the algorithm robust against imbalanced data. Okay, now conclusion is what we do is before after explaining about conclusion, I move to the some practical to show the results also. Okay, we have seen a very few techniques, and why I told you, why I thought you these simple techniques is because you can easily grasp them and apply when you face this kind of data. And simple to mitigate simple algorithms to mitigate class imbalanceness. Okay, so this is how to handle imbalanced data. Okay, so and before I will show you some Jupyter notebook to understand. Okay, there I will try to because I'm spending almost half an hour there. I will explain what are the architectures, how we design the architectures, and how to analyze data exploratory analysis, and how we adapted one of the technique here. What are the technique we used here? We adapted that to improve the thing. See, we see in that practical application, what we see is, see, here I will run another thing. First, let me walk through the Jupyter notebook. Okay. So in this Jupyter notebook is, before proceeding, let me explain overview of this process. Here in this thing, I picked the MNIST data set. There is a mistake, MNIST data set, but this is a uniform data set only. But what I have done is to show you the example. First, I build the algorithm on the uniform data set. So I will set the benchmark. Okay, 99% I got. That is my benchmark. Later, what I did is I made it as imbalance. Randomly dropped the images from the data set and made it as imbalance. And I used this class balance loss function and augmentation, okay, to increase the to reach, because my baseline is 99. Now my objective is to reach that 99 with less number of samples. Okay, so now my object is to reach those things. Now we see that difference is also here. Okay, so this architecture is built. This notebook is prepared on the PyTorch. There are many are there. Okay, so generally many people will use is a TensorFlow and PyTorch. Okay, here I use PyTorch because in the PyTorch we have full control on the different functionalities. Okay, whereas if you use a TensorFlow, it's like a MATLAB only, using APIs and build. Of course, there is there, but we need to do changes in the architect library level, and you can build another application and integrate that. But here it's like our own freedom to do that and change the things as we go on. So this is a PyTorch version. First we imported the libraries, and later we have loaded the data set. Once we loaded, let me here, that is training on. Okay, so once we load the data set, see, let's say we have once we load the data set of MNIST data, we have 28 by 28 image. Okay, it's a gray image kind of thing. I will show you some examples of that. Okay. So here I am splitting the data, 80% for the testing and the remaining 80% for the training. Okay, 20% for testing, validation data. And while training, there are different parameters. Batch size will be there, 32 batch size. Okay, so based on the batch size also, this is the one of the hyper parameter that we can see in the deep learning. There are two kinds of parameters. One is learnable parameters. Those are called learnable parameters. Though on those learnable parameters, we update the weights. Okay, like weights of the neural network comes under learnable parameters. There are non-learnable, but we can adjust that. Those are hyperparameters like batch size, number of epochs, okay, number of batches, okay, learning rate, those kind of things. So those are batch different things here. Batch size. Now we see the data visualization, then we will understand some data points. Here, these are the digit data set, MNIST digit data set, which contains 0 to 9. Okay, 0 to 9, which contains, it's a gray image. Now we define the architecture, but before going there, let me show you the distribution of the data, then you will understand. Oh. Oh. Sorry. Both are same only, but this is to show you how the training process will go. I will change it there. See, these are the distribution of the data. So we have 10 classes. 10 classes, each class is having, there is an imbalance, but this ratio is very negligible because we have enough number of samples. Hardly 2000 samples to build a simple neural network is enough. Okay, yeah, okay. So here, if you see, this is the class distribution. Each image has a minimum above the 5000 images. Okay, but there is a slight change in the imbalance net, but it is fine. Okay, this is how we do the imbalance-ness in the distribution, data distribution, and see identify any major imbalance here is there or not. Okay, in that way we do imbalance-ness. Now we see the architecture changes. Here we define the architecture. If you see that architecture we define here, we have 3 layers as a convolution. We can increase depending on. Suppose we can define as many as. Suppose if you take VGG 19, it has 19 layers. If you take ResNet 50, ResNet also there are different layers. Are 51 is there, 101 is there. Google Net it has more than 150 layers. Okay, depending on the layer, as number of layers are increases, you need more number of data because we have more number of parameters to learn, right? So as number of layers increases, so we need to increase more number of data at the input. So initially we used because you see any deep neural network has two kinds of layers. Number of layers might be variant, but minimum two kinds of. One is convolutional layers, that is to understand, to learn the features. Before deep learning, what we used to do, we used to do conventional image processing, features extraction, statistical features, shift, surf, okay, ORB features, Asian features. It's a lot of full human crafted. Those are human crafted features. But whereas deep learning, we don't need to worry about the features to craft the features because there is a convolution layers. It will try to it will try to extract features from the input based on the target itself. Okay, it will learn itself and it will try to extract suitable features for the specific task. Okay, that's why these convolution layers are used. And the other thing is, once you extracted the features, you need to convert that into the feature descriptor to make to train machine learning algorithms. Okay, like SVM and HOG kind of, okay, sorry, SVM kind of thing, and random forest decision trees. Okay, those kind of algorithms to make learn those algorithms, we will use features. They're either handcrafted features or maybe deep learning crafted features. So by using these features, now we need to convert that into the feature descriptor. For that, we use as a linear layers. That is called fully connected layers. Okay, these fully connected layers are used, okay, to make as a class. This acts as a classification algorithm. See, first layer will convert that into the 2D vector to the 1D vector. After that, you can reduce the dimension of the after converting 1D, the dimension will be more. Okay, what we need to do is we need to reduce the dimension. So for that, we use other layers here. Okay, and the final layer will act as a classifier. Okay, but altogether will act as a classifier, but at the final layer we will make the prediction. Okay, here my input dimension, say from 64 input data of 2D into converted into 128 dimension. Now I use this 128 dimension. You can build other algorithms, SVM. You can train SVM also. Okay, you can train decision tree, random forest, XGBoost kind of things. But here I use as a 10 class classifier output layer, right? Okay, that is, and this forward function here, two one is defining the architecture. Once define the architecture, at in between, what we need to do is we have activation maps like ReLU activation we have used. Okay, and at the output, generally we use softmax or sigmoid. We use that. This is comes under forward pass. Okay, so once we do that, if you want to see layer wise information, how many layers are there and what is their sizes, here 3 convolution layers we are having. Okay, and after these 3 convolution layers, we have max pooling, reduce the dimension, and these 3 fully connected layers. That means 3, 3, 6, 7 layers. Our architecture is giving, now my deep learning architecture is 7-layer deep learning architecture. So now we have seen the input data and we define the architecture. Now we define the loss function. So once the loss function, now we have seen input and the architecture. Now we need to define the loss function because we need to work on these 3 parts, right? So these 3 parts defining the loss function. So initially I use a class entropy class loss function because I have enough data. So for that I have used this. And this optimizer, why use this optimizer is how quickly you want to make your algorithm to learn. Okay, this optimizer will decide. Here learning rate is learning rate is 0.001. This generally we use from 0.001 to 10 e power minus 6 up to e power minus 6. We select this. Again, this is another research selecting the best optimizer. Okay, automatically selecting the best optimizer, and there is another research. Those are called as iPropt, and those are different algorithms are there. Okay, auto selection of the algorithms. Okay, these are the loss functions. So once you define input, architecture, and the loss function, then you need to train the model by feeding the input data. Okay, this is the batch wise number of epochs I built 30, and after doing that, this is the architecture level definition of the architecture learning process, training process. Once training is done, if you see the epoch number learning loss, if you look at the loss, initially it is more as number of epochs. If data is clean and enough, your loss is start reducing as number of epochs increases. At the same time, the accuracy starts increasing. Okay, validation, both validation and training loss. Here we almost reach 99% at the fifth epoch itself. Okay, so sometimes we reach early if data is good and clean, because Amnesty is very clean data and very well crafted data. That's why we reach this. By using any architecture, we reach at the initial epoch itself. We see whether it is going to be increased or not. So this is how 30 epochs helped me to reach 99. And if you see the accuracies, 99 and 99 validation. And if you want to see, now these are the major things, plots of loss curve and accuracy curve. See, this is loss is start reducing, but here if you see validation loss increasing. But if you see, because we have built 30 epochs, right, you can see there is a smart up here, but it is okay, but variation is very less. If you vary, it starts increasing till further, then you can see there is a suspect. Here also, if you see the last above 98 only, there is no drop in the, only small minor drop is there, but 99 is good. Okay, acceptable here. Okay, this is the thing how we observe the training loss and validation loss curve and accuracy curves we use to predict the learning process and to analyze the learning process. Actually, these fluctuations you may observe, you can think there is a change in the data, input data. Okay, huge change in the data. If whenever network sees unseen data in the training process, there you will get higher loss. Okay, less accuracy. Again, in the next epoch, it will try to adjust that. And this is the function to, I haven't used augmentation because this is conventional method. Majorly I built class balance loss function to see the effect. Okay, so this is the function to do the augmentation, random rotation, because here at the input level we made the augmentation to increase number of images, right? Random rotation, random horizontal flip, and random affine transformation, normalize. See, you may think, what are the algorithms, what are the augmentations we need to build? Again, it is application specific. Okay, so some algorithms possibility of output product. Okay, it will be rotated differently, or it may be flipped cases. Okay, selecting the augmentations also matters. Sometimes you build all the augmentations to increase number of samples. Again, the algorithm will fail to learn. So you need to select the best augmentations to suitable to the application. Okay, what are the real scenarios that may come into in the production? Okay, this is the augmentations we do. After that, now what we do is this we have seen class distribution. Now what we do is intentionally we drop some random number of images from the input data set. Now build the class balancing loss function. So for randomly dropping that, what I have taken is for each class random percentage I have taken, how many number of samples I need to consider. Okay, maybe drop from the input image. You see, instead of dropping also, I can select number of samples. See here only 5% for 0 class and 10% for class 1. Okay, with the existing images, and 5% and 15%. Okay, these are the percentages I defined to select the number of classes, random number of samples for each class. Okay, class ratios. So based on that, I build the functionality to select the number of classes. See, if you see the training shape is 5,000 images I have picked for this training. But if you see at the input, original data, oh, not printed here. Okay. So anyway, we see the distribution. After dropping, see overall 5,000. You have seen previously, each class is having 5,000 images. Okay, that means 10 classes, 50,000 images, above 50,000 from the class distribution. Let me go there. I will explain that is the way. See here, each class is having above 5,000, right? That means 10 into 5,000, 50,000 images. But when you see here, the training number of images are hardly 5,000. Overall, it is 5,000. Okay, now how to make? If you run same algorithm with the same last parameter, you will end up with the less accuracy. Okay, but here we try to use class balance and loss function and achieve our algorithm beautiful to give batch acceptable performance. Okay, so same thing here. See, if you see the distribution, it's hardly 1200. Highest is 1200 only. But if you see remaining cases, it's a 200 images here and maximum 200 only, because 0.05%, right? And if you see there is a huge gap. One is 1200 and there is 200. Okay, almost almost six times difference is there. Highest class to lowest class. Okay, that means we can say now our data is very highly imbalanced. Now we see the class balanced loss function to implement. Okay, data is loaded. Here we use the class balanced weightage. How much weightage you want to give, balanced weightage based on the number of samples for the each class. Okay, you take those classes and you will you will compute the balanced weight parameter for the each class. How much weight I need to give. This is the weight parameter. After that, if you see the same network here, I use the same network, 3 layers and 3 fully connected layers and 3 convolution layers, 1 max pooling layer. No, there is no change in the architecture. Okay, there is no change in the input. Only I'm concentrating on the loss function only. Okay, only I changed the class balance loss function. Okay, from the cross entropy loss function to class. Of course, here also class, but weight parameter I added extra. Okay, only I added extra weight parameter. Okay, after adding here, same architecture, same training model, same training kind of thing. Okay, only feeding is the imbalanced data. Now I'm feeding imbalanced data. Okay, see, if you look at see here, almost I reached the same performance, 96. Okay, here again, if you increase and if you change hyperparameter, it will increase, but I don't want to change anything to show you the difference. With less data and imbalanced data, we are almost able to result in the same performance as the with high data, same architecture, and equal number of samples for each class there. But here we have very minimal data and same architecture, same parameters, and nothing is there. Only thing is imbalanced data we provided as input, and we are able to achieve the same performance here. Okay, and after that, see the performance here and average. Now if you see, it is somewhat beautiful than the previous thing. The class balance, because of class balance, there is a less fluctuations at the input. Now it is following the trend as a training data. Here also it is following the trend as that loss also. Same trend it is following here. Okay, now this is the effect of imbalanceness. Though there is a change in the imbalanced data, but class balance loss function try to mitigate and try to achieve the desired performance and tried to mitigate the issue of imbalancedness. So this is how this class balance loss function works here and helped us to achieve the desired performance. Right? If you calculate the accuracies, See, 96% and validation 92. Of course, it's okay because we did the initial experiment, right? We can change the parameters and make it improve. And if we add augmentation at the input, we haven't added any augmentation. Now, if you add augmentation again, it will try to increase. Okay, so in the same case I told you, right, from 64 to 96, what we have done, we incrementally increased, not drastically increase one time. Okay, it's not spontaneous also. We have adapted augmentation from 64 to we reached 78. After 78, okay, we simply adapted class balance loss function. 78 to 89 we reached. Again, after 89 to we changed the architecture changes. Okay, architecture changes and did some hyperparameter tuning and the network layers, adjusted network layers and reached 96. So this is how we incrementally increased the performance of the system with the imbalanced data. Okay, this is how this is iNotebook, IPython notebook helped to increase that, because I can run on without this also. I didn't find time to build. Suppose here class balance loss function, I thought of running without class balance loss function. Anyway, I will give this IPython notebook to you. You can run on that. Only thing is we need to change. Only thing is either you need to use Google Colab or GPU if you have. Here in my laptop I ran, but it took almost above half an hour to run that. Okay, we try to see that. Okay, this is how this helped this class balance loss function, how to make adjustment and those kind of things. Okay, with this I'm concluding my session. We see that now I try to build. We see because 5 more minutes, 10 minutes are there. I try to run this now. We see, because without using class balance loss function, I try to see that. See here we have changed this, right? Now what we do is I will use a class loss function. 1 second. And let me copy the class loss. Here optimize it. We build the same thing. Nothing we don't do. Take this. Here I will copy this. I don't go in depth about this, but I will try to manage. Here it is there. Now we do the training use. I'm running on CPU. We see we stop after one or two epochs. Now later we move to the questions using. So VS Code is the one of the option to work on Python. See, major things when any deep neural network you want to build application on deep neural network is there are different parameters to work on. One is input data, architecture level, and such kind of things. See, of course, it has given maybe there is a change in the feeding input data test loader. We see that. I will give you this notepad. Notepad, you can explore that. Okay. Let me see that. A bit data loading, I might be change that. Yeah. So now we move to PPT. Yeah. So that's all from my end. Any questions is welcome. And I'm feel see apart from this one, soon I'm going to start one startup AI to build AI agents on that. If you are interested, we can have a small brainstorming sessions kind of thing. Okay. So that's all from my end. Any questions? Let me know. See, after this, I will give you this notepad and PPT. Hello.
Yes, sir. We are to the end. So we'll conclude. And thank you, sir, for your expertise. And all the participants, I request you to come to Lab 105 F Block by 11:30. We'll start the session. It will be offline, so everyone can leave now.
Yeah. Thank you.